Okay, one more time. Everybody, please mute your microphone. Okay, please mute your microphone. Mr. Ibrahim, would you please mute your microphone?
Okay.
Yeah, everybody.
Check.
Have I done so?
Would you please mute your microphone, Mr. Ibrahim?
I'm trying, Prof.
Yeah,
I'm trying.
Yeah. You can see, I mean, if you touch your Zoom on the bottom, maybe on top, you can see here we have like mute microphone, something like that. Can you find it?
Okay.
Yeah. So please mute your microphone, but if you want to speak, if you have any question, then you can raise your hand.
No have any question.
Mr. Jani Puri, you please mute your microphone.
Okay, I am listening now.
Okay, please mute your microphone. You can see here on your Zoom screen, we have microphone, right? Mute, unmute. Okay, thank you. So we are going to start. So if you have, if you want to speak or question, if you have any question, just raise your hand. Okay. So if you remember, last time we discussed up to here, right? Yeah, we had a lemma that we just talk about this lemma without proof. I said the proof is not required, so we just accept it without proof, and I'm not going to ask the proof in the exam also. Okay, so the proof is not required. So let's continue. Right after this lemma, now we have to continue from here. Okay, so slowly, I read and explain for you, and I also, if you need some more explanation, I'm going to write here and explain for you. So should be okay. So we have a remark here. Look at here, CBRN, okay, is a space, denotes the vector or Banach space. If you are, okay, we know that I assume that everybody is familiar with the notion of vector space. So vector space, or beyond that, Banach space of all complex valued bounded continuous functions on Rn, okay? So this is the definition of CBRN. Denotes, look at here, all functions from Rn into C such that f is bounded and continuous, okay? So please write down this definition. Okay. And can you give me an example of a bounded continuous function on R, okay, on one-dimensional space? Okay. Guys, I changed my mind. Since I want you to involve in the discussion, if you would like to, you can unmute your microphone. At first I said muted, maybe because of this noise of environment. So if you are sitting in quiet place, then you can unmute your microphone to speak and to involve in discussion. So if you are sitting in some quiet place, so you can unmute your microphone and speak. So can you give me an example of a bounded continuous function in R, like a function from R into R, real value, which is bounded and continuous? Do you have any idea? Okay. Can you give me an example of a, as I said, you can unmute your microphone. You can speak. Okay. Look at here, for example, function sine x, function sine x. Do you agree with me? This is a function from R into R, which is bounded and continuous, right? So sine x belongs to CB of R. Is one example, okay? Sine x is a bounded continuous function on R, right? From R into R, it is bounded and continuous. It's bounded between -1 and 1, right? Do you remember the values of sine x? So can you give me another example? Huh? Of course, we have a lot of examples. Another example is, if you agree with me, cosine x, right? Cosine x. This is another bounded continuous function on R, okay? From R into R, it's continuous and bounded, right? Okay. Okay. Now look at here. We said that we have this. Do you remember DRN, test function space on Rn? It's a subset of CBRN. Why is it like that? Huh? DRN means the test function space, right? It means the space of all complex value functions which are infinitely continuously differentiable with compact support. So this is a subset of CBRN. Why is it like that? So definitely every test function is continuous, right? Okay. Why is it bounded? Is the question. Why is it bounded? Huh? Do you have any idea?
Hello, Prof.
As I said, you can unmute your microphone to speak if you are sitting in quiet place. So you can unmute. Okay, look at here. The reason is, okay, every test function has a compact support, right? Correct or not? So it means outside a compact set is 0. Since every test function is continuous, right? It maps compact set to compact in C, right? Complex number. So it maps compact to compact, and every compact set is bounded, right? So it means here, look at here, the supremum of the, okay, phi is a test function. The absolute value of phi x on Rn exists. And that actually, this supremum equals the supremum on K. Why is it like that? Why can we take supremum on K? Huh? Because this is a test function, right? Outside its support. Okay, here K is the support of phi, right? Outside K, this is 0. So this supremum reduced to over K actually, okay? So this supremum exists. Look at here one more time, I repeat. Since phi outside K vanishes, right? So, and phi is continuous, the absolute value of phi is also continuous. It maps compact set to compact, but compact in C actually, okay? Because values of phi are coming from complex number. So it maps compact to compact, and compact is bounded, right? So this supremum exists, okay? So every test function is bounded and continuous. So test function space is subset of, okay, CBRN. So here you can see I mentioned, we may write simply like soup, the absolute value of phi x when there is no confusion. Okay. So please make a note if you would like to. Next, we are going to show that actually this test function space has a topology. It means it's a topological space, or more precisely, I don't know if you are familiar with the notion of topological vector space. Of course, we are not going to talk about that, but actually test function space here has a topology, and with that topology is a topological space, or more precisely is a topological vector space. Okay. So now look at here, topology and convergence in DRN. Listen very carefully, okay? The test function DRN has a topology, okay. Now, it has a topology, right? So we want to see that in this topology, if we have a sequence of test function, I mean, how is it convergent to an element of DRN? You can see, I mentioned here, let's say phi m is a sequence of test functions on Rn, is a sequence in this space. Is convergent to an element like phi of Drn, listen very carefully, if there exists a compact set or compact subset of Rn which contains the support of each phi m and phi, okay? So we say that in the topology of DRN, a sequence like phi m is convergent to phi if there is a compact set like K which contains the support of each phi m and phi, okay? And moreover, look at here, phi m and each derivative of phi m of any order, okay? If you are talking about test functions on one-dimensional space, so when we say derivative, it means ordinary derivative. But if you are talking about test functions on dimensions higher than one, so we have partial derivatives. So moreover, each phi m, phi m, and partial derivatives of phi m of any order converge uniformly to those of phi. It means like phi m is convergent uniformly to phi, and each derivative of phi m is convergent uniformly to that one of phi. Like first derivative uniformly to first derivative, second derivative uniformly to second derivative. But let me ask you something. When we say we have a sequence of functions which is convergent uniformly, okay, when we say, for example, let me just explain this one for phi m. So will be the same for each derivative. Then we say, for example, phi m is convergent uniformly to phi. What does it mean? Do you have any idea? You might have seen this when we say a sequence of functions is convergent to, like here, phi m is convergent to phi uniformly. What does it mean? Have you seen this? Okay, I'm going to explain here for you. Okay, you may, if you would like to, you can make a note. Then I'm going to recall you or explain you what does it mean when we say. So remember, like phi m uniformly to phi, and each derivative of phi m uniformly to that one of phi. It means first derivative uniformly to first derivative, second derivative uniformly to second derivative. Okay. So for example, when we say phi m is uniformly is convergent to phi, it means this. You write down first. Okay, look at here. For example, when we say phi m is convergent uniformly to phi, this means, look at here, for every positive epsilon, a positive number like epsilon, there is a natural number like n such that for every m greater than or equals n, look at here, the absolute value of phi mx minus phi x is less than epsilon for all, okay, for every x belongs to Rn, okay? So be very careful, read this very carefully. When we say phi m is, this uniform is stronger than pointwise, okay? I'm going to explain you. It is uniformly, and therefore pointwise. When we say phi m is convergent to phi uniformly, it means for every positive epsilon, there is a positive integer like n such that for every m greater than n, okay, the absolute value of phi m x minus phi x is less than epsilon for every x, okay, for every x. It means this positive number exists for every x, okay? This is the meaning of uniform convergence. And of course, if it is uniformly convergent, then it is pointwise. But the converse is not true. If you have a sequence of function which is convergent pointwise, it may not be convergent uniformly. So be very careful. In fact, like, okay, I don't know how much you are familiar with mathematical logic. If I move this term for every x in Rn here, like for every epsilon positive, for every x there is n, then that becomes pointwise conversion, okay? But when there is one n for every x, okay, that means uniform conversion. Okay, and I think you agree with me about this. Now look at here, when you say for every x, okay, for every x. First of all, when we say phi m x minus phi x, do you agree with me? This means phi m minus phi, right? This means phi m minus phi at x, and phi is a test function, phi is a test function, phi m minus phi is also a test function. So look at here, when we say for every m greater than n, look at here, we have this for every x. So it means epsilon is an upper bound for this, okay? So you agree with me, we can say for every m greater than n, the supremum of this is less than equal to epsilon. You agree with me? Look at here, this means for every x we have phi m minus phi at x is less than epsilon. So epsilon is an upper bound, okay? So when you say supremum, it means least upper bound. The supremum of this, of course, it exists and is less than equal to epsilon, okay? So we can say like this, phi m is convergent to phi if for every epsilon positive, there is a positive integer like n such that for every m greater than n, the supremum of the absolute value of phi m minus phi at x is less than equal to epsilon. I hope you are familiar with these notions of the uniform convergence and pointwise convergence already, because these are like our preliminary background required for this course. And that is something from mathematical analysis, not function analysis. Okay, now look at here. It's very important. Be very careful. Furthermore, moreover, okay, you accept it without proof. At least you know this. In this topology, it means the topology of DRN. DRN, the test function space, is a topological space. We already explained that it has a topology, and we talk about convergence of the sequence. In this topology, every Cauchy sequence is convergent. Okay, it means if you have a Cauchy sequence of test functions, then it is convergent. Second, very important, this topology is not, be very careful, is not induced by any norm or metric. It means DRN, okay, is a topological space, okay, but it's not metrizable. Okay, it's not metrizable. It means this topology on DRN that we explained. Let me back show here. You remember we said that it has a topology. This topology of DRN is not induced by any norm or metric. That's why, look at here, that's why, do you remember I said here this supremum exists? Do you remember here? Let me explain you something about this, why I did not mention norm. Okay. So I have to explain you something here. Okay. If you remember, we said that this DRN, test function space, okay, is a subset of CBRN. And we know that CBRN is a Banach space with supremum norm, okay? It means if we have a test function like phi, okay, it's a test function here. So definitely belongs to this. So if you remember, we said that this supremum exists. The supremum of phi x, okay, the supremum of phi x exists, right? Okay. This, okay, because phi is an element of CBRN. Actually, this supremum of phi, when you view phi as an element of CBRN, this supremum is actually the norm of phi. Okay, actually, this is the norm of phi. Okay, the norm of phi as an element of this. But look at here, when you view this test function as an element of DRN with that topology is not coming from any norm. That's why in our note, when we are talking about the supremum of phi, I do not use the norm notation because I don't want you to get this impression that the topology of DRN is coming from norm, okay? If, okay, every test function definitely is an element of CBRN, bounded continuous function. If you work on this space, okay, you can denote this supremum by norm. Definitely this supremum is the norm of phi, okay? But if you are working with a test function space, if you have a test function, when we talk about sup, we do not use this notation. Why? Because I don't want you to get this impression that the topology of this space is coming from norm. No. So we just write sup. We do not use this norm notation. So be very careful. So when you view every test function as an element of this, yes, you can, because it's a Banach space with sup norm. So you can say that this sup equals the norm of phi. But if you are just a study about test function space, we just say sup phi, okay? Do not use the notation norm. This is to avoid confusion because then the topology of DRN is not induced by any norm or metric. That's why here I did not say norm. I just said sup. Okay. So be very careful. Okay. Let me give you an example here. You suppose that phi is a test function on Rn, okay? We've defined a sequence of test functions here, which is conversion to phi. How do we define this? Look at here. Every phi mx is defined to be m over m plus 1 phi x. It means each phi m is actually the scalar product of phi. This is a scalar. And if you remember, we talked in that lemma, the previous lemma. What was that lemma? If I'm not mistaken, lemma 1.7. What was that lemma? Yes. The scalar product of each test function is a test function. Okay. So each phi m is defined to be the scalar product of phi. So definitely each phi m is a test function. We can show that this sequence of test function is conversion to phi. Okay, it's conversion to phi. Okay, in the topology of DRN. I leave it to you to check the details. However, I'm not going to ask you. But at least look at here. If m approaches infinity, look at here. If m approaches infinity, this limit is going to be 1. So at least we can see that each phi m is conversion to phi pointwise, but actually uniformly. You have to show it. Okay. This is one thing. Another point is that okay, if k is the support of phi, then this k contains the support of each phi m. Okay. As I said, this is an example. I'm not going to ask you to prove it. At least see one example of a sequence of the elements of DRN. It means sequence of test function, which is conversion to an element in DRN, a test function. So each phi m is defined to be the scalar product of phi. It means like this. Okay, m over m plus 1 phi. Definitely each phi m is a test function. And we can show that this sequence of test function in Rn is convergent to phi in that topology of the Rn. Okay. Is there any question so far? Please feel free. If you have any question, just feel free to ask. So next we are going to define the distributions, okay, which are actually continuous linear functionals on test functions space. Okay. Shall we go to the next definition, which is the definition of distribution or generalized functions? Okay. Definition 1.11. Okay. You suppose that f from DRN into C is a linear functional. Okay. We already gave you the definition of linear functional. this DRN is a complex vector space. When we say we have a linear functional on DRN, it means a linear map from DRN into C. Okay. Now look at here. We say that F is continuous. Listen very carefully. We say that F is continuous if Pm is convergent to phi in DRN with the topology of DRN that we explained just now. So if Pm is convergent to phi, then F of Pm as a sequence in complex numbers, okay? Look at here, the values of F are coming from complex numbers. Then F of Pm as a sequence of complex numbers is convergent to F of phi, which is a complex number. So simply, you have a linear functional on DRN. You say that this F, this linear functional, is continuous if Pm is any sequence in DRN which is convergent to phi, then F of Pm as a sequence of complex numbers is convergent to F of phi. Now, what is a distribution? You can see a continuous linear functional on DRN is called a distribution or generalized function in DRN. Okay, so when we say we have a distribution in Rn, it means we have a continuous linear functional on DRN. It means a continuous linear map from DRN into C. And the continuity is in this sense. Then the set of all distributions in Rn, is denoted by d prime Rn. And we can show that actually this set of distributions in Rn is a linear space with pointwise operations. What does it mean? You write down first, then I explain. Actually, d prime Rn distributions, the distribution space is actually the dual space of DRN. I don't know if you are familiar with the notion of the dual of topological vector space. So actually, d prime Rn is the dual of DRN. So it means simply the dual of test function space is defined to be the distribution space. Okay. But at least we need to know that the set of distributions, okay, is a vector space, okay, or linear space with pointwise operation. You write down this, then you tell me what does it mean when we say with pointwise operations. So we give you definition, gradually later we give you some examples. So you write down this definition, then I'm going to explain the last two bottom lines. So every continuous linear functional on DRN is called a distribution or generalized function. So now, if you back and take a look at our discussion in the first meeting when we were talking about the motivation behind introducing the distribution, and now you may it might be clearer for you what we were talking about. because if you remember, in the first meeting, we started with the motivation of defining the or extending the notion of ordinary function to generalized function. Okay. Now let me explain this. Look at here, we said that the set of all distributions in Rn, the prime Rn, is a vector space with pointwise operation. What does it mean? This means simply here. Okay, this simply means, look at here, if F and G are two distributions, it means two elements of the prime Rn. Okay, and lambda is a scalar complex. Okay, then F plus lambda G is also a distribution. It means this also belongs to the prime Rn. Okay, F plus lambda G. But how do you define F plus lambda G? It's defined to be pointwise, right? Just like ordinary function. F plus lambda G at X, you tell me, this defined to be what? It's defined to be Fx, right, plus lambda Gx. That's it. So when we say the set of distributions with pointwise operation is a linear space, vector space means this. It means, okay, simply, if F and G are two distributions, F plus lambda G is also a distribution. But how do you define this F plus lambda G? Is defined to be pointwise. F plus lambda G at X, okay. I'm sorry. Just here I have to make a, doesn't matter, but here because every distribution maps a test function, right? So we have to say that actually here for the argument, we have to say, let me correct this, because every distribution, it doesn't matter, we can use X, but here X is not an element of Rn. X is a test function. But since we are using like phi psi for test function, so we have to say like this. Let me correct it. It's not wrong, it's correct actually, but like this. F plus lambda G at phi, okay? If you say X, there's no problem, but we have to be careful. X must be a test function. Okay, phi equals F of phi, right? Plus lambda G of phi. Okay, for every test function phi. Again, there is nothing wrong if you say X, but when you say X, be careful, X must be a test function. But since we are using this notation phi for test function, so this is better. So F plus lambda G at phi, F phi plus lambda G phi. So this is this means pointwise. Okay. Okay. So distributions form a vector space or linear space. Okay, you make a note, then we continue. Okay, let's back here. Now, next we have a theorem. Okay, I'm going to mention this theorem without proof. The proof is not required. Actually, first when I mentioned this theorem, then later it appeared to be not so useful, okay? Because it involves some strong condition. I mean, so it is like, how to say, too strong to apply to show the continuity of linear functions, but there is no harm. So I just mentioned explain without proof. However, proof is very easy, but the proof is not required, okay? So it means I'm not talking about the proof, and I will not ask the proof in the exam. You suppose that we have a linear function like f on Drn. This linear function is continuous if there is a positive real number like m such that, look at here, the absolute value of f of phi is less than m times the sup of the absolute value of phi x, okay, for every phi, for every test function, okay. So if you have a linear functional which satisfies this condition, then f will be continuous. It means if there is a positive real number like m such that the absolute value of f of phi is less than m times sup, absolute value of phi x, you can see this sup is being taken on the support of phi, okay? Basically on Rn, but it will be reduced to support of phi for every phi, okay? As I mentioned, this is not so useful, I mean, the theorem, okay? You are going to see later, actually, when we are talking about the distributions, when we give you some examples, when we want to prove the continuity, we are not going to use this theorem, okay? Okay, but there is no harm. So just make a note of this theorem, bear in mind without proof. Is there any question so far? Okay. Okay. Now we are going to give you some examples of distributions. Okay, listen very carefully. Starting with this. Every continuous function like a from Rn into C induces a distribution like f sub a in Rn. It means f sub a, it means the distribution is an element of D prime Rn, such that, look at here, so fa is if you want fa to be a distribution, right? It means it must be a continuous linear functional from Drn into C. And fa is defined to be, look at here, look at the formula. Fa maps every test function like phi to, look at here, integral ax phi x dx, or simply integral a phi. And of course, this is a multiple integral. When we say on Rn, we have n single integral. This AX means A of x1, x2 up to xn, d of x1, x2 up to xn, dx1, dx2, dxn. Okay, like if we are talking about one-dimensional one integral, two-dimensional double integral, three-dimensional triple integral. Okay. Of course, we are going to show that this is indeed a distribution. It means we have to show that FA is a continuous linear functional. It means we have to show the linearity and continuity of FA. Linearity is easy. Okay, I just quickly mention, I leave it to you because linearity of FA follows from the linearity of integration. Okay. So remember, every continuous function induces or can be viewed. If you look at our discussion on motivation of defining the distributions, now that discussion there should be clear now by this definition. So every continuous function like A from Rn to C induces or can be viewed, or I would like to say induces a distribution like Fa on Rn in Rn, like it means a linear function like Fa from Drn into C by this formula. It maps every test function here to integral A phi. Okay. Like in particular, in one-dimensional space, okay, in one dimension, in particular, okay, this is in general in n-dimensional space. In particular, in one-dimensional space, like Fa. So when we are talking about one-dimensional space, A is a function, a continuous function from R into C, okay? Fa maps every phi, every test function to integral A phi, okay? You can see one-dimensional, one single integral, which means this. Okay. So remember, every continuous function on Rn, it means every continuous function from Rn into C induces a distribution in this form, okay, in this form. We are going to prove that. It means we are going to prove that Fa is a continuous linear functional. Okay. When we are talking about one-dimensional space and we say, okay, every continuous function induces a distribution, can you give me, of course, we have a lot of examples. Can you give me some examples of continuous function on R? You can see I provided here. We have a lot of examples. For example, you can see if you take Ax to be exponential minus x, sine x, cosine x, and so on, it means you can see each one is a continuous function, so induces a distribution in this form. For example, like here, if Ax equals exponential minus x, in this formula, we put Ax to be exponential minus x. So it means F maps every phi to integral exponential minus x phi x dx. Okay. And of course, look at here. You might wonder that, okay, this integral is improper integral. So if this if Fa wants to be well defined, this integral must be convergent. This is the first thing that we have to check, that we are going to show in general for n-dimensional space. Of course, we are going to show that Fa is continuous and linear. But before that, we have to show that Fa is well defined. It means this integral here in one-dimensional, or this one in the n-dimensional, must be convergent, right? Okay. Look at here, I mentioned something here. Fa at phi, it means the value of Fa at phi might be denoted, okay, if you refer to some other textbook, they may denote this by this, like this, almost like inner product, A and phi, okay? But for our discussion, we use this notation. But if you refer to other textbook, for the value of FA at phi, they may use this notation. Like look at here, if you view A as a, how to say, let me explain you here. Like it would be good to repeat what we said from the motivation. Okay, let me explain this for you. Okay, it doesn't matter. Let me put a line, explain here. Like, look at here, if you view A, okay, A is a continuous function, okay, from Rn into C. From Rn into C. So if you view A in the ordinary notion, so we have AX, for example. But when A induces a distributions, okay, it means a continuous linear functional from drn into C, then this A maps every right test function to a complex number, right? Like it maps every test function to a complex number. That value might be denoted by this, A and phi, like this. It means here we are using the ordinary notion. Here we are viewing A as a distribution, okay? Something like this. But as I said, in our work, the distribution induced by continuous function and other type of the functions like locally integrable that we are going to discuss about, use this notation, FA, to stress that, okay, F is a distribution induced by A. We do not use this notation. Okay. Okay. Let's back to the previous page. Okay. Here. Okay. So now listen very carefully. Again, we said that every continuous function induces a distribution of this form, right? Okay. So we are going to show that first. This FA is well defined, okay? Linear and continuous, okay? Here, if you are ready. So what you are going to see is about how to say, to show that FA is well defined. It means this integral is convergent. Okay. Okay. Look at here. I said, firstly, note that since A is continuous, right? And okay, suppose that E is the support of phi is a test function, is compact, then there exists a positive number such that the absolute value of AX is less than L for every X in E. Why is it like that? Do you have any idea? Why is it like that? So we are going to show that that FA that we define is a continuous linear functional. But before that, we have to show that FA is well defined, starting with this. Okay, A is continuous and E as the support of phi is compact set. So there is a positive number such that we have this. Why is it true? Do you have any idea? Why is it true? E the support of phi as a subset of Rn. Why is it true? Do you have any idea? If you have any idea, feel free to speak out. Okay, I'm going to explain you. Simply, but I'm going to write. Look at here, A is continuous, right? The absolute value of A is also continuous. And continuous function maps the continuous function, map compact set to compact. So every compact set is also bounded. So this is true, right? Let me explain here with more details here. Okay. Oh, look at here. A from Rn into C is continuous, right? Okay. So this is continuous. CONT, continuous. Now look at here. If we have a function like Rn, if you have a function from Rn into C defined by this, look at here, defined by this, which maps x to the absolute value of Ax. This is actually the composition of A and the absolute value. So absolute value is continuous, A is continuous. So do you agree with me? This is a continuous function. This is a continuous function. Now, this is a continuous function. Let me write here. Continuous function. Or even I don't need to write like this, okay? Here, I mean, it's enough. I don't need to make details like this. A is a continuous function, right? Okay. Now look at this. E as a subset of Rn, E as a subset of Rn is compact. E as a subset of Rn is compact. And look at here, continuous function maps compact set to compact. So it means this set, look at here, be very careful, this set, look at here, this set. Okay, it means the set of Ax, X belongs to E as a subset of what? As a subset of what? As a subset of C, right? It's compact. You remember from mathematical analysis or topology, continuous function maps compact set to compact. Okay, let me erase here. Okay, we need some more space. Okay. Okay. Now look at here. So we said that this set Ax, the value of x on E as a subset of C is compact, right? And C is a metric space. So every compact set is bounded. It means if you move here, this set is as a subset of C is bounded, okay? bounded. Bounded. Okay. So when we say this set is bounded, what does it mean? It means as a subset of it means there is a positive number like L such that st means such that the absolute value of ax is less than equal L less than equal L for every x in E. Correct or not? So one more time. A is a continuous function. E as a subset of Rn is compact. So A maps compact to compact. So this as a subset of C is compact. Therefore, it's bounded. Do you remember every compact set is bounded? It means this is as a subset of C is bounded. When we say bounded, it means this. There is a positive number such that the absolute value of AX is less than equal L for every X in E. That's the reason. Simply, continuous function maps compact to compact, and every compact set is bounded. That's the reason. We need this to show that fa, our function is well defined. If you remember, in every metric space, every compact set is closed and bounded, right? We are using that fact. Remember here, when we say this set, look at here, this set. It's actually the image of E under A, right? This is A of E actually, correct or not? Compact, A of E is compact. Okay. So now we know why. So we have this, okay? Next. Therefore, look at here. Thus, we have the absolute value of integral a phi on Rn equals the absolute value of integral on E. Look at here. Here, integral from Rn reduce the integral on E. Why is it like that? What's the reason here? E is the support of phi, right? Outside outside E, phi vanishes, okay? Phi is 0. So this integral reduced to integral on E, correct or not? Because look at here, what is E here? The support of phi, right? E is the support of phi. So outside E, phi is 0, okay? So only left integral over E. This is one point, another one. Now look at here, the integral of a phi on E is less than the integral of absolute value. Okay, here from here to here, we are using the property, some property of integration that says the absolute value of integral is less than the integral of absolute value. So this is less than the integral of absolute value of a phi, and the absolute value of a phi equals absolute value of a times the absolute value of phi dx. Okay. You write down up to here. Now next we have to say why do we have this? Okay, you write down up to here. Okay, now look at here. Next, we have the integral absolute value of phi a, absolute value of phi dx is less than sup absolute value phi of x, integral absolute value a dx. Why do we have this? From here to here, what is happening? Why do we have this? I'm going to explain you. Because this sup is an upper bound for these values, right? And it's a constant value, can move out of integral, but I'm going to explain for you. So I'm going to explain you what is happening from line 2 to line 3. Why do we have this? Okay. Okay. Let's move to this page. Mr. Ibrahim, there is some noise in your microphone. Okay. Okay. Now let me explain you what is happening here. We have to erase our board. Mr. Ibrahim, somebody's microphone is making noise. Please mute the microphone. Okay. Okay. So we are going to explain why do we have this. Look at your line 2. So we have here integral absolute value ax. Okay. Absolute value phi x dx on E. Okay, we want to show that this is less than sup. Okay. Here, look at this. Do you agree with me that the absolute value of phi x, the absolute value of phi x is less than or equal? Okay. Yes. Less than or equals sup the absolute value of phi x for every x on E. For every x, okay, sorry, for every x in E. Remember, this supremum is being taken on the support of phi, which is E. Okay, do you agree with me about this? Because this is an upper bound for this value, right? It means for every x in E, the absolute value of phi x is less than the sup, right? Because this is an upper bound. Okay. Now, if you agree with me, now, can I multiply both sides of this inequality by absolute value of AX, which is some non-negative value, so it doesn't change the direction of inequality. So if I multiply both sides of this by AX, so I have the absolute value of AX times the absolute value of VX, is less than the absolute value of AX times sup, the absolute value of phi x. Correct or not? I multiply both sides of this with absolute value of AX. Now look at here. This is true, right? For every x on E. Now, the value of the, and look at here, this is a non-negative function, okay? So it means this is greater than or equal to 0. So we have this inequality between the values on the values of two positive functions, okay? So by the property of integration, look at here, on E, the values of this function is less than this, okay? So we can integrate on both sides. Next is this, okay? Or if you want me to do it separately, next we are going to integrate on both sides. It means since like let's say f is less than g, the integral of f is less than integral of g. We are using the property of integration. So the integral of absolute value of ax, absolute value of phi x dx, okay, on E is less than equal the integral, the absolute value of ax okay times sup the absolute value of phi x on E dx. Now look at here, do you agree with me? This sup absolute value of phi x is a constant number, right? It's a constant value, can move out of integral, okay? There is a constant like C. This one can move out of integral, right? So when this moves out of integral, we get this. Look at here. So it means then this sup can move outside integral because this is like a scalar, like alpha, can move here. So you write down this, so that's the reason. So simply, for every x in E, the absolute value of phi x is less than this. This is some upper bound, some constant, like alpha. So you multiply both sides by the absolute value of ax. So f is less than g, the integral of f is less than the integral of g. Now, this is a constant value, moves outside integral here. So if you want me to write down, okay, you just come here. So then we get sup absolute value of phi x times the integral of the absolute value of ax on on E dx. Okay, so you get this. Okay, this is A. Okay, this is A. Let me write it. Get her here. This is A. Okay. Okay. So we have this. Now, so we have this is less than this, and then look at here, again, something's happening. Now, this value is less than this. So look at here, L, this is our L, remember. L integral of 1 dx on E. Again, why do we have this? What is happening from here to here? Very similar to this, okay? I'm not going to repeat, but I explain you quickly. What is happening? Why do we have this? Okay, this is the same, right? These two are the same. Look at here, very similar to this discussion. On E, the values of the absolute value of AX is less than L, right? Look at here. On E, we have the absolute value of AX is less than L. So you just integrate on both sides. Integrate on both sides. When you integrate on both sides, L is a constant, moves outside integral, right? So you get this. You get sup L integral 1 dx on E. Okay, but I have to explain you something. I don't know if you are familiar with at least little bit with measure theory of integration. This integral of 1 dx on E is actually measure or the Lebesgue measure of the compact set E, which is finite. Okay, so we get sup L ME. Whatever, if you are not familiar with the measure theory or integration, you just know that this integral of 1 dx on E is something finite, which is actually the Lebesgue measure of the compact set E. For example, look at here in one-dimensional space. If this E is the closed interval A and B, then integral 1 dx on interval A and B will be B minus A. Okay, so you write down this first. I explain you more in the another page actually. So remember, this integral 1 dx on E is actually the measure, with actually more precisely, the Lebesgue measure of the compact set E, which is finite. Whatever, this is something finite. So we have the product of these three values here. So you can see this integral is finite conversion. So FA is well defined. Okay. You can see I mentioned. M is the Lebesgue measure of the compact set E. If you are not familiar with the measure theory, that, sorry to say this, I think unfortunately many of you, as far as I know here, are not familiar with this. You just know that this integral 1 dx on E is a is finite. This integral is a constant. For example, let me explain you here. Okay, let me explain you this here just quickly. Okay. Let me explain this, then we go for a break. Look, for example, for example, in one-dimensional space, when we say integral dx, you suppose that our compact set is this, like E is this. Look at here, the closed interval A and B. Okay, for example, I just want to explain you. When we say integral 1 dx on E is this closed interval. This means simply integral from A to B dx, right? And this is equal to what? B minus A, the length of integral. Actually, the length of the integral here will be the Lebesgue measure of this closed interval or compact set, okay, which is finite. Something like this. I just try to explain you by some simple example on one-dimensional space. For example, if E is this closed interval, which is a compact set, then the integral on E, it means B minus A. B minus A is the length of the interval, which is actually, if you are familiar with the measure theory, this will be the Lebesgue measure of this closed interval. So at any rate, just bear in mind that this is some constant, okay? So you can see, so we have shown that so far, this integral is convergent, okay? So FA is well defined, okay? So FA, it means our linear, our functional, okay? Our functional is linear. Next here, so this is well defined, okay? This is well defined here, sorry, in dimension. Next, we are going to show that it is linear and continuous. So therefore, it's a distribution in Rn. Okay, next here. But let's have a break because we start almost like at 9:30, 9:11. Let's have a break about 15 minutes. Then we will be back after break. So, by the way, during this time, if you have any question, feel free to ask. Okay, so let's have a break, about 15 minutes, then we continue. Is there any question? So let's go for a break, 15 minutes, then we will be back. Okay, if you are ready, let's continue our discussion. Okay. Mr. Muhammad, you want to see the definition 1.9. Okay. So definition 1.9. Here's the definition 1.9. Okay, Mr. Muhammad, this is for you. You asked to see the definition 1.9. Okay. So if you would like to make a note, you make a note of this definition.
Okay, I've taken.
Okay, already? Okay, no problem.
Thank you very much.
No problem. Okay. Now, where are we? Okay. Okay, here. So we saw that FA is well defined. Now, look at here, our linear functional, okay, this one. Now, we are going to show that there is a continuous linear functional, okay? So first, the linearity. I'm gonna leave it to you, okay? The linearity of FA follows from the linearity of integration. It's easy. I leave it to you, okay? So use the linearity of integration to show that FA is linear. It means here you have to show that for, let me show you. It means you have to show that, okay. You have to show that FA, okay, we have to show that FA, phi, okay, phi plus lambda psi, okay, phi and psi are two test functions, and lambda is a scalar, equals FA phi plus lambda FA psi. This is very easy. I mean, this follows from the linearity of integration. So you prove this. I leave it to you. It's really easy. Let's not to waste any time about this. So you have to show that. So FA is linear, and linearity of FA follows from the linearity of integration. Okay, I leave it to you. Now the continuity, the main point, the crucial point is here to prove that it's continuous. Okay, you can see here, let's back to here. Yeah. Now, it is easy to see that FA, okay, here there is a typo, FA phi, no, FA only, okay, there is a typo. FA is a linear functional on DRN, okay, there is another typo here. Sorry about that, fix it. So it is easy to see that FA, okay, remove this, delete this. FA is a linear functional on DRN, okay, because we are talking generally, okay, not only one dimensional. And the linearity follows from the linearity of integral, okay? So fix it. FA is a linear functional on DRN, okay? Therefore, we only show that it is continuous, okay? It is, we just, okay. Do you remember, if you want to show that FA is continuous, you have to suppose that if phi m is a sequence of test function which is convergent to phi in Drn, okay, then fa of f phi m is convergent to fa of phi, okay? Let me show you. You are going to show this for continuity, that if phi m, okay, is convergent to phi, okay, in Drn, then fa phi m is convergent to fa of phi. We have to show this for continuity of A. So we suppose that phi m is convergent to phi in Drn, then we have to show that fa phi m is convergent to fa phi, okay, as a sequence in complex number. Okay. So suppose that phi m is convergent in Drn, from which it follows that, do you remember when we say we have a sequence of test function is convergent to convergent, what it means, right? There exists, recall the definition. There exists a compact set like K, compact subset K of Rn, which contains the support of each phi m and phi m and every derivative of phi m, okay? Phi m and every derivative. Okay, here we just use phi m. Phi m and every derivative of phi m converges uniformly to phi. Okay, do you remember this? Okay, so you make a note. So phi m is convergent to phi in Drn. So we know that there is a compact set which contains the support of each phi m and phi m, and each derivative of phi m is convergent to that one of those one of phi. It means phi m is convergent uniformly to phi and every derivative of phi m also. But we are going to use only this, okay? Okay. Okay. Now, I said then, since there exists a positive number such that the absolute value of AX is less than L for all X in K. Why is it true? Just not something similar to this we explained, right? Look at here. K is a compact set. A is a continuous function, right? So continuous function on compact set are bounded, okay? You remember just now I explained something very similar to this or exactly like this. So since since A is a continuous function and K is compact, it maps compact to compact and every compact set is bounded. So there is a positive number such that the absolute value of AX is less than L for every X in K. And therefore, okay, you write down this. Let's see what happens. So we are going to show that FAFM is convergent to FAP, right? So it means this sequence is convergent to this. So we have to show that the distance between these two can be smaller than any positive number if M is large enough, right? Okay. Okay, let's see what happens here. Okay. Now look at this, the absolute value of FAFM minus FAP. Okay, here we are using the linearity of FA. So this equals the absolute value of FAFM minus P, because prior to this, we already showed that it's linear, okay? Now, this equals the absolute value. Okay, what is the formula of FA? Integral, it maps every test function because Pm minus P is a test function. Integral A Pm minus P, or more precisely AX times Pm minus P at X dx. And look at this. This equals integral on K. Look at here. We have on Rn becomes on K. Why is it like that? Look at here. Everything the same. But here we have integral on Rn now becomes integral on K. You have any idea? It's easy. Let's back here. You remember we said that K contains the support of Pm and Phi. What does it mean? It means outside K, Pm minus Phi is 0. Outside K, Pm is 0, Phi is also 0. Okay, so Pm minus Pm is 0 outside K. So this integral reduced to integral on K, because outside K, the value of this function is 0. So equal this. Now, from here to here, we are using the property of integrals, the absolute value of integral less than the integral of absolute value. Okay, so this is less than equal integral on K, the absolute value comes here, less than the absolute value of AX times the absolute value of Pm minus Phi at X. And look at this. This is less than this. Look at here. We have less than sup integral. Look at here, sup. Something similar to this we explained just now. Do you remember when I was talking about when we were talking about when we were talking about showing that FA is well defined? We explained something similar, right? because when you say soup of these values on k, this is an upper bound for this, okay? So it's a constant, moves out of integral, okay? Something similar to this just now we explained. So this is less than soup integral, the absolute value of x on k. Now look at here, again, something similar. This is less than soup L times integral 1 dx on k. Why is it like that? Why do we have this? Look at here. This integral is less than L integral 1 dx over k. Similarly, look at here. L is an upper bound for this value. It means, look at here, for every x on in k, the absolute value of ax is less than L, okay? You just integrate on both sides, huh? So now, L is a constant, moves out of integral, so you get this, okay? So you get soup L integral 1 dx on k. As I mentioned, integral 1 dx on k will be the Lebesgue measure of the compact set k, which is finite. You may imagine that k is a something like closed interval or closed box, actually, because we are talking about n-dimensional space. At any rate, if you are not familiar with the measure theory, you just bear in mind that the integral 1 dx on k is something finite, a constant. So you get this. This is less than soup L m dx, or you call this C or alpha, anything. Positive, okay, this is a positive value. Next, we are going to use this fact that Pm is conversion to phi uniformly. So it is uniformly. So if this m is large enough, this will be smaller than any positive number. So totally, look at it, this will get smaller than any positive number, which means the distance between these two can be smaller than any positive number if m is large enough. That means that Pm is conversion to Fa phi, right? So it means it's conversion to, and f is continuous. Okay, we are going to show this. So you write on up to here, then I explain. Next, we are going to use this fact that Pm is conversion to phi uniformly. So this soup can be smaller than any positive number if m is large enough. Okay. Okay, now look at here. Pm is conversion to phi uniformly, right? So there is a positive integer, right? Such that this soup, like if you take any positive number like epsilon, then there is a positive integer such that for every m greater than n, this soup, right, can be less than epsilon, right? Pm is conversion to phi uniformly. So for any positive number like epsilon, there is a positive integer such that for every m greater than n, right, this soup can be smaller than this epsilon, correct or not? And therefore, we get this. Do you remember from this calculation. We get the absolute value of FA Pm minus FA Phi is less than this sub Lm, right? Okay, now look at here. Here, we get this, okay. We have this, right? Now, if M is large enough, which means this, then this sub can be smaller than any positive number. So this is less than, it means when we say M is large enough, it means there is a positive integer such that for every M greater than N. This sub is less than epsilon. You can see this sub is less than epsilon. The rest is the same, L, M, K. So you can see, look at here. Again, this is some positive number. So you can see, when we say the absolute value of FAPM minus FAP is less than this, so it means the distance between these two can be smaller than any positive number. Again, this is another positive number. You may take it like epsilon prime. So this means the distance between these two can be smaller than any positive number if M is large enough. Now, what does it mean? It means this sequence of complex numbers is convergent to this. It means FA Pm is convergent to FA Phi. And what does it mean? It means FA is continuous. It means we show that whenever Pm is convergent to Phi in DRN, in test function space, FA Pm is convergent to FA Phi in complex number. And that means FA is continuous. So we are done with this example. So we can see we try to elaborate everything. We show that first FA is well defined. Linearity is easy. I left it to you. And this is the continuity. Okay, some more example. So bear in mind, every continuous function like A induces a distribution in that form. It maps every test function to integral A phi. Okay, look at here. So we said that every continuous function, right, induces a distribution. This continuity somehow is a strong condition. We want to define some distributions in the similar fashion, in the similar way, but under some weaker condition. It means, okay, we already saw that if the function A is continuous, it induces a distribution. But can we have the same story, but like A is not continuous? It means, can we have the same story under weaker condition? Like if the function A is not continuous under some other condition, weaker condition, can we still have some distribution of the same form? Okay. You can see here, we want to define some distributions in a similar way to example 1.3, it means this one, under some condition weaker than continuity. Okay, weaker than continuity. It means we want to weaken the continuity condition. Continuity condition is too strong. So we want to weaken the continuity condition so that we have a larger set of distributions of this form. Okay. So we want to define this. So for that purpose, we mean to define the distribution similarly under weaker condition. We need this definition. Okay. 1.4. Look at here. A function like A from Rn to C is called locally integrable if the integral of the absolute value of dx on K for every compact subset okay, is finite. It's conversion. Okay, so we say that a function like a from Rn to C is locally integrable if the integral of the absolute value of a on every compact set or every compact subset of Rn is finite. We are going to see that every locally integrable function induces a distribution similar to this example. And of course, we are going to see that when we say the local integrable, this is a condition much weaker than continuity. We are going to see that actually every continuous function is locally integrable. It's very clear. You should be able to show this. But we are going to mention. But the converse is not true. So every continuous function is locally integrable, but not every locally integrable is continuous. We are going to show this by some example. So bear in mind this definition. Shortly later, we are going to see that every locally integrable function induces a distribution in a similar fashion to this example. And of course, when we say the function is locally integrable, this is much weaker than continuity. Okay. Can you give me some example of locally integrable function? Okay, I have provided some example here for you. Actually, we have a lot of examples. It's easy. Okay, you can see here. For example, this function, let's say function f from R into R defined by fx equals, for every x between -1 and 1, 1 minus the absolute value of x or modulus x, I don't know what do you call it, absolute value or modulus. Otherwise, 1/2. This is an example of a locally integrable function. I just roughly by a graph, I explain you why it is locally integrable, but I leave it to you to check the details. It's easy, like a bit playing with calculus, integration and calculus. So it shouldn't be a big deal. So you make a note. Let's see the graph of this function. Then roughly I explain it on graph. Okay, shall we see the graph of this function? Here. Okay, let me just close it and open a new page, not to waste the time for erasing. Okay. I think it's easy for you. Let's see the graph of this function. Okay, I try to sketch here for you, and this is like okay, this is let's say this is y-axis, this is x-axis. Okay, look at for every x between 1 and -1, the absolute value of x, okay, we have minus, goes up here. So if here is 1, okay, and here is 1/2, okay, and here is 1, and here is -1. So this will be the graph of this function. Look at here, we have like this. Okay, we have roughly. one more try. Okay, here, MT, not actually, because this, is it correct or not? Okay. Let me see what it did. Between 1 and -1. Okay. So, no, here, I got confused, something simple. We have 1 minus the absolute value of x. Okay. The absolute value of x is like this. If minus, shift up become like this. Okay. Here. Okay. Okay. Let me erase this one. Okay. I got confused. Something very simple. Okay. Between 1 and -1. Okay. It's easy. This is minus absolute value of it. It goes up here. Here. So we have here like this. Okay. Empty here. Here also empty bullet. And then outside this will be 1/2. So here we have like this. Okay. Here also we have like this. Correct or not? Okay. And here is, you can see 1/2, 1/2. I hope the graph is clear for you. Okay, this is the graph of this function. Okay. Okay, we have, you can sketch the graph by translation. Okay, this is minus absolute value of x, shift up here. Okay, here is empty bullet, and here, okay, it's correct. So now look at here. This is the graph of this function. Roughly, I'm going to explain that this function is locally integrable. We call it f, right? So it means we have the integral of absolute value of fx, the absolute value of fx on every compact set as a subset of R here, okay? Every compact set is finite. Okay, look at here, just roughly speaking, but I leave it to you. You agree that if we consider any compact subset of R, this compact subset of R can be contained, because it's bounded, can be contained in some open or closed interval. It doesn't matter. Okay, even K could be a closed interval. So you agree with me? Okay, let me make it closed. It doesn't matter. If I take any compact set in R, since it is bounded, it can be contained in some closed or bounded. Okay, make it closed, subset like AB. Now, if you consider the integral of this function on every closed interval like this, for example, here is AB. You can see like here A, here B, for example. Since in every interval like A and B, the function is bounded, so definitely this integral will be finite. So this is roughly some explanation to see that why this function is locally integrable. Because if you calculate the integral of this function on every open or closed, it doesn't matter, okay? Let's say closed. interval like a and b, like this, bounded interval, okay, like this, okay, you may take here a, b, or here a, b. This integral will be finite. So this shows that this function is locally integrable. This is some explanation, okay? It's not exact proof, but if you want it, you can, as I explained, you can prove it, and the proof is just playing with integral in calculus. So shouldn't be a big deal. Okay. So check this, that integral. Then because we have f is a subset of the, like can be contained in any closed interval. So we have the integral of f simply on k is a subset of integral of f on closed interval a and b, which means integral from a to b, okay? And this is finite, okay, for every closed interval. So this will be finite. So this shows that the function is locally integrable. Okay. Okay, another example. Let me explain this. We have a remark here, it's very important. Yeah, this is easy to see that every continuous function is locally integrable, but the converse is not true. Every continuous function is locally integrable. Why is it like that? But the converse is not true. It means not every locally integrable function is continuous. Example, this one, you can see. So be very careful. I'm going to explain for you. Every continuous function is locally integrable, but the converse is not true. It means not every locally integrable function is continuous. This is an example. You can see this function is locally integrable, but it's not continuous. Okay. Now, you tell me why every continuous is why every continuous function is locally integrable. Okay. Now you explain me this. Let me again close this one. So this is an example. You can see this is a locally integrable function which is not continuous. Now, you give me, okay, now you tell me why every continuous function is locally integrable. Why is it like that? It's easy. Actually, you have seen it just now. Right here, if A is continuous, in general, let's say f from Rn into C is continuous. We claim that this is locally integrable. What does it mean? It means the integral of the absolute value of AX the integral of the absolute value of AX on every compact set is finite. Why is it like that? Just now we mentioned something. Do you remember? Okay, look at here. Since A is continuous, right? It maps compact to compact, and compact in C is bounded, right? So it means since A is continuous, on K is bounded. It means there is a positive number like L. Just now we mentioned such that ST means such that the absolute value of AX less than equals L for every X in K. Now you integrate on both sides. Okay. So when you integrate on both sides, the integral, let me write simply, integrate on K, okay? The integral, the absolute value of A on K less than of integral L on K, and this equals L integral on K. It means actually integral dx over K, okay? And do you remember we said that this is something finite because integral 1 dx over K, this is the Lebesgue measure of the compact set K, which is finite, okay? Like this. So you can see every continuous function is locally integrable. So A is bounded on K, you just integrate on both sides. And this one equals L times integral 1 dx, and this is a finite, okay? This is finite, okay? Because this means the Lebesgue measure of the compact set K. So you can see every continuous function is locally integrable, but the converse is not true. Not every locally integrable function is continuous. Not. Okay. Okay. Another example. Every characteristic function, okay, look at here. You suppose that E is a subset of Rn, in particular open, but it doesn't have to be open, okay? For example, if E is a subset of Rn, the characteristic function of E is defined to be, look at here, is defined to be like this. It's a function from Rn into R. If X belongs to E is 1, otherwise 0. This is the characteristic function of the subset E of Rn, in particular open subset. We claim that every characteristic function is also locally integrable. I'm going to discuss this with you. And then we have a theorem. You can see every locally integrable function induces a distribution. Then this is enough for today. Okay, so I don't know if you are familiar with the characteristic function. So if E is a subset of Rn, in particular, if E is an open subset of Rn, then chi E, chi sub E, this is some Greek letter, chi E. Okay. From Rn into R is defined to be, look at here. It maps every X. If X belongs to E, 1, otherwise it means if X does not belong to E, it means X belongs to the complement of E, it's 0. Now we want to show that every characteristic function is locally integrable. You write down this, then I'm going to move to another page, to our board, something like that, to show this for you. Okay. So let's move here. We are going to show that every characteristic function is locally integrable, right? Okay. So let me again close this one to save the time, open new page. Okay. Okay. Look at here. So we have to show that for every compact set in Rn, for every compact set in Rn, the integral of the absolute value of chi E x, right, dx on K is a compact subset. Okay, compact. This is finite. Okay, we have to show this. Okay, let's move down here. We have to little bit play with set theory. First of all, look at here. Do you agree with me? I can write K. K is a subset of Rn. Can I write K equals K intersection with Rn? You agree with me because this is a subset of Rn. And let me move here. And this equals K intersection. Can I write this Rn as E union E complement? Can I write it like this? Because E is also a subset of Rn, right? I can write it like this. You agree with me? Okay. And by distributive law, we have K intersection E union K intersection E complement. Correct or not? Okay. So now let me put K here. In this, okay, K equals this, right? Okay. Let's put this K here, see what happens. So we have integral the absolute value of chi E, okay, x dx on K okay equals, okay, you write down first. Okay. And look at here. This union is disjoint union, okay? What does it mean when I say disjoint union? It means they don't have intersection. We are going to use some property of integration, if you are familiar. I'm going to use this property. Look at here, when we have integral, simply integral on A, and usually for disjoint union, they use this notation. But anyway, so A disjoint union B, okay? Okay. By the property of the integral, this equals integral on A plus integral on B. We are going to use this property from integration. Here we have disjoint union. When I say disjoint union, look at here, okay, this is union, right? For disjoint union, we use this notation. And when we say disjoint union, it means A and B does not intersect, okay? Empty, it's empty set, is empty. Okay, is empty set. So if we have the integral on A disjoint union B, the union of A and B, and they do not have any intersection, they do not intersect, the intersection is empty set. Then by the property of integration, we know that the integral on A disjoint union B equals integral on A plus integral on B. So we are going to prove this. We are going to use this. Okay. Now back to here. Look at here, your K, here your K. It's the disjoint union of these two sets, right? Disjoint union of these two sets. So this integral will be the integral, the absolute value of chi E, okay, x dx on k intersection E plus integral absolute value chi E x dx on k intersection with E complement. Okay, I'm sorry for interruption. Okay, E complement. Okay, what is next? Do you have any idea what is next? So k is the disjoint union here. So this integral on k, you can see k, is integral on k intersection E plus k intersection E complement. This is the complement of E complement. So what is next? Do you have any idea? Okay. Now you tell me, what can you say about this integral? What is the value of this integral? I claim that this is 0. But why? Can you tell me why? This integral is 0. Why is it like that? Look at here, k intersection E complement. Do you agree with me? This is the subset of E complement. It's a subset of E complement. It means here x does not belong to E. Okay, when x does not belong to E, the value of this function is 0. Okay, so this integral is 0 actually. This integral is 0 because we are integrating on k intersection E complement. This is the subset of E complement. Okay, so it means E belongs to E complement, does not belong to E. So the value of this function is 0. Now, what about this? What about this? Look at here, k intersection E is a subset of E. So here x belongs to E. When x belongs to E, the value of function is 1. So this value of the function becomes 1. So only left integral 1. Okay, 1 dx over k intersection E. 1 dx intersection E. Okay. So here x, this is the subset of E, x belongs to E, so the value of the function is 1, so left this. Okay, let me erase some part. I believe that we do not need, we don't need this. Okay, let me erase, then we use some. Okay. Now let's move here. Okay, let's move here. Okay, let me show you. So let's move here. Oh, now look at here. We have integral, let me repeat it again, integral dx over k intersection E. We are almost there. Okay, now look at here. Do you agree with me? K intersection E is a subset of K, right? This is a subset of K. This is a subset of K, correct or not? This is a subset of K, okay? Again, by property of the integration, since K intersection E is a subset of K, and here we have non-negative function, okay, 1. So this is, by property of integral, is less than integral 1 dx over K. Integral 1 dx over K. This is by property of integration. K intersection E is a subset of K, and 1 constant function is non-negative. So by the property of integration, we have this. Now, this integral is finite. Again, why? As I mentioned, because integral 1 dx over K is the Lebesgue measure of the compact set K, which is finite. For example, if if this is some closed interval, so this will be the length of the interval, this integral. So you can see. So we have shown that the integral, the absolute value of chi e on every compact set is finite. What does it mean? It means the characteristic function of any set E is locally integrable. Okay. So one more theorem, then it's enough for today. So next we are going to show that every locally integrable function, you remember previously we said that every continuous function. Now we are going to mention the same thing, similar things actually under weaker condition. We are going to show that every locally integrable function induces a distribution in similar way using the integration. Okay. Shall we move to next? Okay. Here. So this is our last thing for our discussion today, then it's enough for today. Okay. Theorem. Every locally integrable function like a from Rn into C induces a distribution Fa, you can see similar to that example for continuous function, such that it maps every test function phi to integral a phi dx for every test function. So you can see we define a similar, the distribution in Rn under weaker condition. Here A is locally integrable. Might be continuous, might not be. It doesn't matter, but it's locally integrable. Okay. So you make a note of the statement of the theorem. Here we are going to prove it. It means we have to show that it's well defined and linear, that I'm not going to repeat, because to show that it's well defined and linear is very similar to the, you can see example 1.3. We just verify the continuity. Okay. It means you have to show that it's well defined and it's linear. I'm going to leave it to you because it's easy. It's similar to that example 1.13. And then we just show that Fa is continuous. You can see I mentioned here, the proof is very similar to the discussion in example 1.13. It can easily be seen that Fa is linear. So I'm going to leave it to you to show that Fa is linear, okay? Linearity follows from the linearity of integration. very easy. So let's just see that FA is continuous. Even the proof of continuity again is similar to example 1.13, but just some almost some let's say minor difference, because here we are using the fact that A is locally integrable rather than continuous. But totally is very similar. You are going to see. Okay, look at here. We want to show that FA is continuous. Again, we have to show that if Vm is convergent to Phi in DRn, then FA of Vm is convergent to FA of Phi in complex number. Okay, very similar. So you suppose that Vm is a sequence in DRn which is convergent to an element of DRn like Phi. Okay, from which it follows that, again, we are going to repeat the same thing. There is a compact set, blah, blah. Okay, you write down up to here. So you suppose that Phi is convergent to Phi in DRn. Okay. So a moment, sorry, let me for our need, maybe let me, okay. 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 So suppose that Phi is convergent to Phi in DRn, from which it follows that, again, look at it, there exists. Okay, from which it follows that there exists a compact subset like K of Rn, which contains the support of each Phi and Phi, and Phi and of course each derivative of Phi is convergent uniformly to Phi. Okay, it means Phi and each derivative of Phi. Okay, but here we just use this fact that Phi is convergent uniformly to Phi. Okay. So there is a compact set, contains the support of each Phi and Phi converges uniformly to Phi. Okay. Then, since A is locally integrable, you remember when we were talking about continuous function, we said since A is continuous, then we have a positive number like L, then the integral of A is less than the integral of L, blah, blah. But here it means we reduce the condition to locally integrability. So since A is locally integrable, okay, look at here. What is K here? K is a support, sorry, K is a compact set. Since A is locally integrable, the integral of the absolute value of AX dx on K is something finite, like A, correct or not? Because A is locally integrable. So integral of the absolute value of A on every compact set, including K, is finite. So you suppose that this integral is A. And therefore, now we are going to show that, look at here, FA phi m is convergent to FA phi. It means the distance between these two can be smaller than any positive number if m is large enough, which means that this is convergent. This sequence of complex number is convergent to this. Okay. Okay. Therefore, now look at here. The absolute value of FA phi m minus FA phi, okay, FA is linear, okay? We already suppose that we prove it. I left it to you. So FA is linear, we can say the integral, this equals, sorry, the absolute value of FA phi m minus phi. And this equal, you can see, is very similar to that example. The absolute value of, okay, what is the formula of FA? Integral on Rn ax times phi m minus phi x dx. And again, this integral is reduced on k because k contains the support of each phi m and phi. So it means outside k, both are 0. So this function outside k is 0. So only left integral on k. And again, by the property of the integration, the absolute value of integral is less than the integral of absolute value. And then again, look at here. This is less than this sup, because this sup is an upper bound for this, right? So you integrate on both sides. I explained this, very similar. So this is less than sup integral the absolute value of ax dx on k. Here you can see why we use this condition, that a to be locally integrable, because we need this integral to be finite. Okay. Now look at here, since a is locally previously when a was continuous, we said that, okay, because a is continuous, it maps compact to compact and is bounded, so we get this integral finite. But that condition, the continuity condition, was too strong. We reduce it to locally integrability. Okay, so now since a is locally integrable, so this integral is something finite like a, you can see here. Okay, now the same story. Since phi m is convergent to phi, similarly, since phi m is convergent to phi uniformly, if m is large enough, this can be smaller than any positive number. So totally, this can be smaller than any positive number, which means this is convergent to this. So write down this one first. So this integral equals a, something finite, and of course non-negative, because we are calculating the integral of some non-negative function. Okay, absolute value. So a is positive or non-negative. Sorry. Okay. Now look at here, we have this, right? So we have the absolute value of this one is less than this. Now look at here, since phi m is convergent to phi uniformly, so for any positive number like epsilon, there is a positive integer like n, such that for every m greater than n, we have this sup is less than epsilon. Okay. And now look at here, this is less than this. We prove it here. This is less than this, and when m is large enough, this is less than epsilon. So again, epsilon times a is another small positive number like epsilon prime. So you can see here, if m is large enough, the distance between these two can be smaller than any positive number. Okay, what does it mean? This means this sequence is convergent to this. And that means fa is continuous. So you can see that every locally integrable function induces a distribution in a similar fashion to continuous function. But note that not every distribution arises in this way, okay? Today we ran out of time. Okay, next week I'm going to give you some other example of distributions in other form. Okay, not every distribution is of this form. Next week we are going to talk about Dirac delta distributions, which is of the different form. So remember, not every distribution arises in this way, like using integration like that. So FA is continuous. So that's enough. You can see we continue next week with Dirac delta distribution, which are distributions of other form, not in this way. So that's enough for today. Do you have any question? Okay, I'm going to stop the recording, and I can share this file with you on Dropbox, perhaps on Dropbox, because I don't think so it's possible to send it by email, because by Gmail, like maximum we can attach a file with 30 megabytes. So I have it. So if you have a Dropbox, I can share it with you. Okay. So now stop recording.